Okay, let's just jump right in. If you work anywhere near tech, engineering, finance, honestly, any field that uses a computer, you're dealing with numbers all day, every day.
Right. Dollars, inventory, vacation days, whatever.
Exactly. But those numbers are almost always in the system we all learned as kids, decimal, base 10.
Hmm.
So today, we're going to go deeper. We want to move past that and really crack the language that the machines themselves are actually using to get things done.
That's the mission, isn't it?
It is. In this deep dive, our goal is to give you that foundational mastery, the stuff you need to really understand how a computer calculates. And this isn't just theory.
No, not at all. This is the nuts and bolts.
If you're prepping for a technical exam or you're writing a memo that has to be super precise with its numbers or, you just want to be genuinely informed, this is it. This is your masterclass on binary, octal, hexadecimal, and the one that always trips people up, binary coded decimal.
And I think you framed that perfectly. We're going to take a very methodical, almost a professorial approach here.
Right.
We're starting at square one. We'll define every single piece of jargon, and we'll build up step by step, column by column, into the arithmetic and the conversions.
So it's not about just memorizing a chart of numbers.
Absolutely not. The goal here is for you to master the rules, the mechanics, the cause and effect of it all. Because in digital logic, you can't be mostly right. Precision is everything. So let's start by laying that solid foundation, figuring out what makes a number system tick.
Okay, so if we're going to talk about numbers, we have to start with the smallest possible idea, the single thing. So what is a unit?
A unit is just that. It's a single object. It's the concept of one. One apple, $1, one pulse of electricity. It's our starting block.
And from there, a number is just a symbol we use to represent one or more of those units.
Exactly. A symbol or a collection of symbols.
Simple enough. Okay, now for the big one. The concept that holds this all together. The base, or as it's sometimes called, the radix.
Right. The base is the absolute cornerstone of any of these positional number systems. And it tells you two incredibly important things right away.
Okay.
First, it tells you the total number of unique symbols the system uses. And second, it tells you the grouping number for when you have to carry over to the next column.
So if we look at our familiar decimal system, that's base 10. And of course, we use 10 symbols for it, 0 all the way through 9.
And if you see base 2, or binary, you immediately know you only have two symbols to work with, 0 and 1.
And it's always true that the biggest symbol in any system is one less than the base itself.
Exactly. And that idea leads us directly to the most important concept we're going to cover today, positional notation.
Okay, this is the big one.
It is, because this is what explains why the ones in the number 11 in decimal. So 11, 10, and dollars are completely different from the ones in 112, 2 in binary.
They look the same, but they mean very different things.
Wildly different. Positional notation is the rule that says the value of a digit isn't just about the symbol itself, like the number 4, but where it's sitting relative to the separator.
And that separator has a universal name, doesn't it? We call it decimal point, but it's really the radix point.
Yes, exactly. It's the anchor. It separates the whole numbers on the left from the fractions on the right.
So each position, each slot for a number represents a power of the base.
That's the key. Each position is a power of the base, and that power is called the exponent. If you really truly get this for base 10, you'll get it for every other base we talk about. The rules don't change.
Okay, let's ground this. Let's use an example in base 10 that we all know. How about 427.5?
Perfect.
So the 7 is in the first spot to the left of the radix point. That's the $100 position. So 7 times 1 is just 7 units.
Right. The one it's called.
Then the 2 is in the 101 position. So 2 times 10, 20 units.
Mm-hmm.
And the 4 is in the 122 position. 4 times 100, 400 units.
And what about that 0.5 on the other side, the fractional part?
Well, that's in the first spot to the right, so it must be a negative exponent. It's the $10 position.
Meaning 5 times 1/10.
Right.
Or half a unit. That's the whole structure. And when we switch to base 2, we just swap out all those 10s for 2s. We go to base 16, they become 16s. The architecture of it stays exactly the same.
Okay, so since the position is what gives a digit its value or its weight, we need a way to talk about the endpoints. The most important digit and the least important one.
We do. We need to define the most significant digit, or MSD, and the least significant digit, LSD.
So the most significant digit, the MSD, is the one that has the biggest impact on the number's total value.
The greatest effect, exactly. It's the leftmost digit that isn't a 0.
And conversely, the least significant digit, the LSD, has the smallest effect on the overall magnitude.
It does. It's usually the one on the far right, though its exact position depends a little on if you're looking at a whole number or a fraction.
I think the easiest way to really feel the importance of this is to look at the role of zero.
Yes.
Zero isn't just nothing, it's a placeholder. If you take a number like 6 of Taizo 5.47, that zero is critical. It's holding the 6 in the hundreds place.
That's the cause and effect right there. If you take that zero out, the number becomes 65.47. The 6 shifts from the hundreds place to the tens place.
From representing 600 units down to just 60.
And that's a massive difference of 540. You took out a nothing and changed the value enormously. That zero is essential for keeping every other digit in its correct weighted position.
And for anyone doing technical work or, prepping for an exam, being able to spot the MSD and LSD in a flash is fundamental. It tells you where the real value is and where things like rounding errors might creep in.
Let's do a quick check if you see the number 420.
Okay, 420. The MSD is obviously the 4. It's got the most weight. What about the LSD?
Well, since it's a whole number, the LSD is the digit right next to the implied radix point, so it's the 0.
Okay, but what if the number is a fraction, like
Right.
0.0024? Now where's the MSD? My gut says the first 0, but that has no value.
Exactly right. And that's why the definition is the leftmost non-zero digit, because that's the first digit that actually contributes to the magnitude. So in 0.0024, the MSD is the 2.
And the LSD, the one with the least effect, is the 4 at the very end.
Correct. That distinction is so important when you're reading, say, a data sheet where precision is everything.
Okay, so quick recap. We've got our fundamentals down. Unit, number, base, positional notation, radix point, MSD, and LSD.
And the key takeaway is that the base tells you how many symbols you have, and positional notation is the rule book for how those symbols get their value using powers of that base.
We have our universal language rules.
We do. And now we can use that scaffolding to start building with the actual languages of computing.
All right, now we're getting into it. The computer's native tongue, the binary number system, base 2. We're going from 10 symbols all the way down to the bare minimum.
We are. The binary system uses just 2 symbols, 0 and 1. And the cause and effect here is all about the hardware. It's purely architectural.
Because computers are just a massive collection of switches.
At their core, yes. And a 1 and a 0 are perfect for representing the 2 possible states of a switch. A 1 can mean on, or active, or there's an electrical pulse. A 0 means off, inactive, no pulse.
It's an unambiguous direct mapping from the number to the physical state of the machine.
Which is why it's the native language of every digital device.
And since the base is 2, all that positional notation we just talked about now relies on powers of 2. So 2101 is 2, 2101 is 2, 22 is 4, and so on.
And the fractions work the same way. 2 to 1 is a half, or 0.5 in decimal. The rules are the same, just the base has changed.
Okay, we need to pause here for a huge misconception alert.
Yes, this is important.
Because we are so wired for base 10, our brains can trick us. A number like 10110 is 101. That's a decent-sized number. But 11222 looks the same.
But it's tiny. It's 1 times 22, which is 4, plus 0 times $21, which is 0, plus 1 times $2, which is 1.
So 4 plus 0 plus 1 is just 5 in decimal.
Exactly. So you have to use the little subscript, like 1012d2, to specify the base. Especially in any kind of technical document or memo. Context is everything.
All right, let's move to the heart of what a computer does, arithmetic. Starting with binary addition. It seems simple with only 2 digits, but the complexity comes from the carry, doesn't it?
It does. First, let's just quickly define our terms. We have the augend, which is the first number, the addend, the number being added to it, the sum, which is the result, and the carry, that extra digit that gets generated.
Okay, so what are the rules?
There are only 4, and they're built around those 2 symbols.
Let me guess. 0 plus 0 is 0.
Rule 1, correct. $2 plus arrow 2 is 02.
0 plus 1 is 1.
Rule 2.
1 plus 0 is also 1.
Rule 3. And now, the most important one.
1 plus 1.
$12 plus 12 plus 12 was 122.
Ah, so it's not 2. The result in that column is a 0, and you generate a carry of 1 over to the next column to the left.
That's the trigger. That's the binary equivalent of 9 plus 1, giving you 0 and a carry in base 10. It's the mechanism for shifting to a higher position.
Okay, let's walk through an example slowly. Let's add 112 to 2 and 112 2.
Okay, in decimal, that's 11 plus 13. So we should get 24 as our answer. Let's see if the process works.
All right, we'll start on the far right, the $20 bill position. We have 1 plus 1.
Which is 102.22. So we write down the 0 and carry the 1.
Okay, next column, the 201 1 position. We have our carry of 1 plus a 1 from the top number plus a 0 from the bottom.
So 1 plus 0, that's another 102 to 2. Write down 0, carry the 1.
Moving left again to the 202 and 2 position, a carry of 1 plus a 0 plus a 1.
Again, 1 plus 0 plus 1 is 102 2. So write 0, carry 1.
And the last column, the 203 return position, we have a carry of 1 plus a 1 plus another 1.
Now this is interesting. 1 plus 1 plus 1. That's 3 in decimal, which is written as 122 2 in binary.
So we write down a 1 in this column, and we carry another 1 over into a new fifth column, the 24/704 position.
Exactly. And that carry just drops down. So our final sum is 101,022 Taurus.
Let's check it. The positions are 1, 2, 4, 8, 16. We have a 1 in the 16's place and a 1 in the 8's place. 16 plus 8 is 24.
The procedure works.
But what happens if you have to add, say, 4 ones in a single column, like from multiple add-ins? The sum is 4 in decimal.
Right. And 4 in decimal is 1,000 and 1,022 Annabelle in binary.
So the sum in that column is a 0, but what about the carries?
You generate 2 of them. You have to carry a 1 into the next column to the left, the 2111 position, and another 1 into the column after that, the 2222 position.
Wow. So the circuitry inside the chip has to be able to handle passing multiple carries at the same time.
It does, which shows that even though it looks simple, the underlying logic can be more complex than what we're used to in decimal.
Okay, so quick recap. Binary uses raise and ones, powers of 2. The absolute key rule for addition is $12 plus 12 equals 102.2. That's the carry. And we have to remember that adding multiple ones can create multiple carries. That's a big takeaway for anyone tracing digital logic.
All right, let's pivot to subtraction. Same idea. We have the minuend, the subtrahend, the difference, and this time, the borrow.
And again, 4 basic rules. I'm guessing the first 3 are pretty straightforward.
They are. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. No surprises there.
But then we get to rule 4. 0 minus 1.
2 else 12 did. To do that, you have to borrow. And the most important thing to get your head around is what exactly you are borrowing.
In decimal, when we borrow, we're borrowing a group of 10. So here, we must be borrowing a group of 2.
Precisely. You borrow a 1 from the next column to the left, which reduces that column's value by 1. And that borrow brings a value of 210, which is written as $102 into the column you're working on.
So the problem $2.22 becomes $102.12.2.
Which is $12.2. So the result in that column is 1, all because of that borrow.
Okay, let's try a simple example with a borrow. Let's do 101 is array 2 minus 11,002 twice.
Okay, right, most columns. 0 minus 0 is 0. Next column, 1 minus 0 is 1. Next, 1 minus 1 is 0. So far, so good.
And now we get to the 203 position. 0 minus 1. We have to borrow.
We borrow from the 1 in the 2442 column, so that one becomes a 0. Our current 0 becomes 102 to 2.
So 102 to 2 minus 12.2 is $12.2, and the last column is just 0 now.
The result is 017122, which, let's see, 8 plus 2 is 10 in decimal.
Perfect. That was clean borrow. But it gets much, much messier when you have to borrow across zeros.
Yes. This is a classic exam-style problem. Let's try to subtract $12.2 from 1,202.
Okay, well, in decimal, that's 8 minus 1, so the answer has to be 7, which in binary should be 0, 100, and 122. But getting there manually looks tricky.
It's a chain reaction. We start at the rightmost column with 0 minus 1 we need to borrow.
But the next column is a 0, and the one after that, we have to go all the way to the left.
All the way to the 2323 position. We take that 1, which turns that position into a 0. That borrow moves right, turning the 222 position into 102.2.
But we still need to get the borrow over to the rightmost column.
So we borrow from that 102.2. That leaves a $12.2 behind in the 22.2 position and sends a borrow of 102.2s over to the 201.1 position.
And we do it again. Borrow from that, leave a 1 behind, and send the final 102 to the column where we actually need it.
Exactly. So now, finally, in the $28 column, we have 102.12.2, which is $12.2. And the 2 middle columns, we're left with a 1.
So the final result is $122.07. Wow. That procedure, that chain reaction, really shows you what the machine is doing under the hood. It's not just subtracting. It's systematically breaking down a higher order number to pay a debt in a lower order one.
But hang on. Let's talk about efficiency, because that's what drives all computer design. That whole borrowing across zeros thing, that seems incredibly clunky to build in hardware.
It is.
We know computers are optimized to do one thing really, really well: add. So how do they cheat? How does a digital circuit use addition to get the result of subtraction?
They use complements. It's a brilliant workaround. A complement is basically a number's opposite in a way. It's the amount you'd need to add to get to the next power of the base. And this lets the machine completely bypass the whole messy business of borrowing.
Completely. Instead of subtracting, it adds the complement.
So in decimal, we have things like the nines complement or the tens complement. What's the equivalent in binary?
In binary, we have the ones complement and the twos complement. And the ones complement is incredibly easy. Just flip the bits. Every one becomes a 0. Every 0 becomes a 1.
And the two's complement, that's the one that's used in most systems, right?
It is. The standard procedure is find the ones complement and then just add 1 to the result.
Is there a quick and dirty way to do that? A shortcut?
There is, and it's perfect for doing this on the fly. You start from the right, from the least significant digit. You leave all the zeros and the very first one you encounter completely unchanged.
Okay.
And then you just flip every other bit to the left of that.
Oh, that's clever.
It works every time.
So let's get to the actual procedure for subtraction using two's complement. This is a core concept in digital architecture.
Okay, it's a 4-step process. Step 1, leave the minuend, the top number, completely alone.
Got it.
Step 2, find the two's complement of the subtrahend, the number you're subtracting.
Okay.
Step 3, add that complement to the original minuend.
So we've turned subtraction into addition.
Exactly. And now for the crucial final step. Step 4, analyze the carry bit. That final carry tells you everything about the sign of the answer.
Okay, let's try an example with a positive result. Let's subtract 3 from 9. So 1,105.2 minus 0 and 112.2. The answer should be 6.
All right. Minuend is 1,102. The subtrahend is 0, 112.2. Its two's complement is 104, 112.2.
Now we add them. 104 and 112.2 equal.
And now we analyze. We start with 4-bit numbers, but our result has 5 bits. That extra bit on the left, that's the carry.
And what does that carry signify?
A carry means the result is positive. You just discard the carry, and the remaining 4 bits are your answer.
And our remaining bits are 0, 100, and 122, which is 6 in decimal. It works perfectly. The hardware just did addition.
Now for the other case, a negative result. Let's subtract 9 from 5. 0, 1,012.2 minus the 1,002. We're expecting negative 4.
Okay. Minuend is 0, 1,012.2. The subtrahend is 11,12.2. Its two's complement is 11,000 and 12,012.2.
Now add them. 0, 1,012.2 plus 11,012.2 is 11,002 times.
And now we analyze. This time, there's no carry. Our result is still a 4-bit number.
And that's the signal. No carry means the result is negative.
But 11,022 isn't 4, it's 12.
Correct. Because the result you're seeing, 11,022, is not the magnitude. It's the two's complement representation of the negative answer.
Ah, so there's one more step.
One more. To find the actual magnitude, you have to take the two's complement of that result.
The two's complement of 11,022 is 11,022, which is 4.
So the final answer is negative 4.
That is just incredibly elegant. That one little carry bit is the circuit sign flag. Carry means positive, no carry means negative. This explains why two's complement is so fundamental. It lets you handle both positive and negative results with just an adder.
It dramatically simplifies the hardware. So we've covered our binary foundation. Now we can move on to the systems that were really invented for human convenience.
Right. Which brings us to octal and hexadecimal. So if the computer only really speaks binary, why do we even need these other higher bases?
It's purely for us.
Yeah.
For human convenience. I mean, imagine trying to read or type a 64-bit memory address in pure binary.
It would be a nightmare. You'd make a mistake almost immediately.
Exactly. So octal, which is base 8, uses 8 symbols, 0 through 7. And it provides a nice compact way to represent binary, because 8 is a power of 2, is 203 through towers.
So one octal digit can stand in for exactly 3 binary digits.
Precisely. It was really common in early computing systems. And its positional notation, of course, uses powers of 8. So 82 twos is 64, 83 3 is 512, and so on.
And doing arithmetic in octal, it follows the same positional rules, but the carry value changes.
The carry value is now 8. Anytime the sum of a column is 8 or greater, you generate a carry.
Okay, let's do a quick example. What is $68 plus 580 others?
Well, in decimal, 6 plus 5 is 11. So we ask, how many groups of 8 are in 11?
One group of 8 with a remainder of 3.
So the sum in that column is 3, and you carry a 1. The answer is $130.81.
Let's try a bigger one. How about $4,568 plus $138?
Okay, right column. 6 plus 3 is 9. That's one group of 8 with 1 left over. Write 1, carry 1.
Middle column. The carry of 1 plus 5 plus 2, that's 8.
Exactly 8. So that's one group of 8 with 0 left over. Write 0, carry 1.
Left column, carry of 1 plus 4 plus 1. That's 6. 6 is less than 8, so no carry.
So the total is $68.81. The process is familiar, but you have to constantly remind yourself that the 10 in your head is now an 8.
And subtraction would work the same way. If you borrow, you're not borrowing 10, you're borrowing a group of 8.
That's it. The principle is universal.
Okay, so that's octal. But hexadecimal base 16 is really the one that everybody in computing needs to know today, isn't it?
Without a doubt. Since 16 is 204 4-dars, one hex digit represents a neat little 4-bit chunk of binary, which is often called a nibble.
And it's the most compact way we represent digital data. But since the base is 16, we need 16 symbols.
We do. So we use our normal 0 through 9, and then we have to add letters.
And this is non-negotiable. You just have to memorize these. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15.
And the efficiency of hex is just. It's obvious when you look at the positional weights. 160 to 82 is 256. 160 to 300 is 4,096 numbers.
Which is why you see it everywhere. Memory addresses, color codes on websites, low-level debugging. It's the language of the machine made readable.
Right. And for hex addition, the same rules apply. Any sum that's 10 or more has to be written as its letter equivalent. Any sum greater than 15, or F, generates a carry of 1.
So if you add 716 and 916, the decimal sum is 16.
Which is exactly one group of 16 with 0 remainder. So the result is 10 to 16. You write 0 and carry the 1.
Okay, let's try a more complex one, because this is where the mental gymnastics come in. Let's add 3 numbers. C1416 plus 19E16 plus BB216.
All right, this is a good test. Let's go column by column, right to left. First, the $160 column. We have $4 plus E plus 22.
And we have to remember that E is 14. So 4 plus 14 plus 2 is 20.
Okay, 20 in decimal. How many 16s in that? 1 with a remainder of 4. So we write down 4 and we carry a 1.
Got it. Now the middle column, 161 $1. We have the carry of 1 plus 9 plus B.
And B is 11. So that's 1 plus 9 plus 11, which is 22.
22. Okay, that's one group of 16 with a remainder of 6. So we write down 6 and carry a 1.
Perfect. Now the last column, 162 $2, we have a carry of 1 plus C plus 1 plus B.
C is 12, B is 11. So 1 plus 12 plus 1 plus 11, that's 25.
25. One group of 16 with a remainder of 9. So we write down 9 and carry a 1.
And that final carry just drops down. So the result is 1964 16.
That's it. It just shows how you have to be constantly translating those letters to numbers in your head as you work through the problem.
And subtraction would be the same principle.
Yeah.
If you have to borrow, you're borrowing a group of 16.
Exactly. So if you had to subtract C16 from 3 tag, you'd borrow, making your minuend 1316.
Which isn't 13. It's 16 plus 3, which is 19. Then you do 19 minus 12.
Right. The borrowed quantity is always equal to the base.
So quick recap on these. Octal is base 8, symbol 0-7. Hexadecimal is base 16, symbol 0-F. The arithmetic is the same, but the carry or borrow value is either 8 or 16. And knowing those AF equivalents is absolutely crucial. Okay, we've set up the individual systems, now we have to build the bridges between them. This is probably the most common task you'd find on a technical exam. Conversion.
It is. And there are really two main scenarios: converting from our familiar decimal system into one of the others, and converting between the systems that are related by powers of 2.
Let's start with converting a whole decimal number. What's the method?
The systematic method is called repeated division.
And the logic here is that if you divide a number by its base, the remainder you get is the digit that belongs in the very first column, the ones column.
Precisely. So the procedure is this. 1, you divide your decimal number by the base you want to convert to.
Okay.
2, the remainder from that first division is the least significant digit, the LSD, of your new number. It's the rightmost digit.
Then you just keep doing that.
You keep dividing the quotient you get by the base over and over until your quotient hits 0. The very last remainder you pull out will be your most significant digit, the MSD.
And you read the answer from the bottom up, from MSD to LSD.
Let's try it. Let's convert $264 to octal, so base 8.
Okay. 264 divided by 8 is 33 with a remainder of 0. So our LSD is 0.
Good. Now take the quotient 33. 33 divided by 8 is 4 with a remainder of 1.
Okay. And now 4 divided by 8 is 0. With a remainder of 4, we've hit a quotient of 0, so we stop.
And now we read those remainders from the bottom up.
1.0. So 400, 1.808 dollars.
That's it.
Okay. Let's try it with hexadecimal because the letter remainders can be tricky. Convert $174 to base 16.
All right. 174 divided by 16 is 10, with a remainder of 14.
And a remainder of 14 has to be written as the letter E. So our LSD is E.
Correct. Now take the quotient 10. 10 divided by 16 is 0, with a remainder of 10.
And a remainder of 10 is the letter A. That's our MSD.
So the result is AE $16. It just reinforces how much you need to have those letter equivalents burned into your brain.
Okay, so that handles whole numbers.
Yeah.
What about the part after the radix point, the fractions?
For fractions, you use the opposite procedure. Instead of repeated division, you use repeated multiplication.
The logic is kind of flipped on its head here, isn't it?
It is. The steps are: 1, you multiply the decimal fraction, just the fractional part, by the new base.
You're okay.
2, whatever whole number pops out to the left of the radix point after you multiply, that's your next digit.
And here's the tricky part. The first digit you get is the MSD, the one closest to the radix point. The order is reversed from the division method.
Exactly. And you just keep multiplying the remaining fractional part until it either becomes 0 or you have enough digits for the precision you need.
Let's try one. Convert $0.625 to binary.
Okay, 0.625 times 2 equals 1.25 thousand. We pull out the 1. That's our MSD.
And we're left with the fraction 0.25. So $0.25 times 2 equals zero balance deficit, and we pull out the 0.
Now we have 50 cents, so 0.50 cents, 2 equals $1.0. We pull out the 1, and now our fractional part is 0, so we're done.
And we read those digits from top to bottom, so 0.10122.
Perfect. But, some fractions that look nice and clean in decimal are actually infinite in other bases.
Like how 1/3 is 0.333 repeating in decimal.
Exactly the same idea. And that can be a big source of rounding errors in computer calculations.
And if you have a mixed number, like 37.625, you just do both methods.
You split it, you use repeated division on the semi-7, repeated multiplication on the 0.625, and then you just stick them back together with the radix point in the middle.
Okay, now for the real time saver. The shortcut that everybody loves on an exam, converting directly between binary, octal, and hex.
Right. And this works because their bases are all powers of 2. $8 is 203, and 16 times is $204. This relationship is what allows us to just group bits together.
So you don't have to go through decimal as a middleman. You can skip the tedious division and multiplication.
You can. So to go from binary to octal, you just group the binary digits into chunks of 3.
Starting from the radix point and moving out in both directions.
Correct. And if you have a group at the end that isn't a full 3 bits, you have to pad it with zeros to make it complete.
Let's try one. A binary stream like 111 117 22.
Okay. Grouping from the right in 3s, we get 101 one another, then 201 another, and we're left with $10 on the far left.
Which is an incomplete group, so we pad it with a leading 0 to make it $700 to right.
Now we just convert each 3-bit group to its octal digit. $710 is 2, $111 is 7, 711 is 1, 101 is 5.
So the answer is $2,700, $100, and $508.
Wow, that literally took 5 seconds.
It's incredibly fast, and it's the same exact process for binary to hexadecimal, but this time you group by 4s.
Let's try Leonard and 1 uttered, 1 art and 1 2.
Grouping from the right in 4s, we get 700 Muller otters, then 1101 Allard, and we're left with a single 1.
So we pad that with 3 leading zeros to make it 1001 uttered.
1001 is 1, 1101 is 13, which is D, and 1111 is 3.
So 1D 3/16. The efficiency is the whole reason we use hex to begin with. It is.
So what if you need to go from, say, octal to hex?
You can't group directly. You have to use binary as the bridge. It's a quick 2-step process.
Step 1, convert the octal number to its 3-bit binary equivalent.
And step 2, regroup that long binary string into chunks of 4 to get your hex answer.
You just use binary as the universal translator between them.
That's the perfect way to put it.
Okay, so after you've done all these conversions, there should always be a final step, right? A way to check your work.
Always. You should validate it by converting your final answer back to decimal. And for that, we use the first method we ever talked about, positional notation.
The power sum. You multiply each digit by its positional weight and add it all up.
It's the ultimate source of truth for any number in any base.
So let's validate that 2C16 we mentioned earlier.
Okay, the 2 is in the 161-1 position. The C, which is 12, is in the 161-1 position.
So that's 2 times 16, which is 32,
Okay.
plus 12 times 1, which is 12.
32 plus 12 is 44. $44. The validation works.
Okay, so that's our final recap on conversion. To get a number into decimal, you use the power sum. To get a number out of decimal, you use repeated division for whole numbers and repeated multiplication for fractions.
And for the quick conversions between binary, octal, and hex, it's all about grouping by 3s or 4s.
All right, that brings us to our last topic. And it's a bit of an odd one, binary coded decimal, or BCD. We've already got binary, octal, hex. Why on earth do we need another system?
Well, BCD isn't really a number system in the same way. It's more of a special coding system. And it was designed to solve a very specific problem for things like old calculators or digital clocks.
And what was that problem?
The problem was dealing with humans. It's easier for simple hardware to handle decimal input and output if it keeps the decimal structure intact.
So what is BCD exactly?
BCD represents each decimal digit 0 through 9 separately, using its own 4-bit binary code.
So instead of converting a whole number like 49 into one long binary string.
You convert the 4 into its 4-bit code, which is 0, $100, dollars, and you convert the 9 into its 4-bit code, 1001 in dollars.
So 49 in BCD is $100 to dollar, 1001 BCD.
Right. It keeps the decimal digits separate. But this leads to a huge misconception that we have to clear up.
BCD is not the same as pure binary.
Not even close.
Yeah.
And it's incredibly inefficient from a storage perspective.
Because 4 bits can represent 16 different values, right? 0 up to 15.
But BCD only used the first 10 of those patterns for the digits 0 through 9. The binary codes for 10 through 15, so $1,000 through $1,100 are illegal. They're invalid in BCD.
Let's use that example of $49. In pure efficient binary, it's $11,110. It only takes 6 bits.
But in BCD, as you said, it's $100, 1001 BCD. That takes 8 bits.
So you're wasting storage space.
You're sacrificing storage efficiency for the convenience of interfacing with decimal-based displays and keyboards. That's the trade-off.
Okay, so if BCD keeps this weird decimal structure, that must make the arithmetic for it really strange.
It's unique, for sure. You start by adding the 4-bit groups together using normal binary addition. Then you have to perform a check.
A check for what? This is the correction rule, right?
It is. You have to check if the result of your addition is valid BCD. And there are 2 conditions that make it invalid.
Okay, what are they?
First, if the sum of any 4-bit group is a number greater than 9. So if you get a $10 and $10 or higher.
That's an illegal code.
Right. And second, if a carry is generated out of that 4-bit group into the next group.
And if either of those things happens, you have to apply a correction.
You do. The correction is always the same.
Right.
You add 6, which is $810 BCD, to the invalid group.
Why 6?
Because adding 6 mathematically skips over the 6 illegal codes and forces the sum to wrap around and generate a proper decimal carry, preserving that base 10 structure.
Okay, let's walk through an example. Let's do $9 plus 6, which should be 15.
Okay. In BCD, 9 is $1,001 to $1, and 6 is $110.
If we add those with binary addition, $1,001 plus $101 is $1,111 front.
And we check our result. $1,111 is 15 in decimal. Since that's greater than 9, it's an invalid BCD code. We have to correct it.
So we take that invalid result, $1,111, and we add 6, $110.
And $1,111 plus $110 equals a $1,001.
A 5-bit number. How do we read that?
The 4 bits on the right, $111, are your new sum, that's 5. The extra 1 on the far left is the carry that moves into the next decimal position.
So the final answer in BCD is 1001, 0101 BCD, which is 15. The correction worked.
It forces the decimal style carry to happen correctly.
Let's try one more, a more complex one, like $60 plus 505. The answer should be 115.
Okay. In BCD, 60 is $110. 55 is a 10111. We add them column by column.
The right columm, the units. $1,000 plus 01011 is 01011. That's 5. That's a valid BCD number, so we leave it alone.
Right. Now the left column, the tens, $310 plus 01011 is 11 in decimal.
Greater than 9, invalid.
So we have to correct it. We add 6 to it.
Right.
1111 equals 1011.
Okay, another 5-bit result. The 4 bits on the right are 1011, which is 1. The extra bit is a carry.
And that carry becomes the digit in the new hundreds column.
So our final result has 3 decimal digits. The final carry is a 1, the corrected tens digit is a 1, and the original unit's digit was a 5.
Giving you dozen 100011 BCD hour, or 115.
Wow. That's a really specific set of rules.
It is, and that really brings us to our final synthesis. You have binary, octal, and hex, which are all true positional systems related by powers of 2. And then you have BCD, which is this special hybrid coding scheme that uses a correction factor of 6 to force binary arithmetic to behave like decimal arithmetic.
So after all that, we've really achieved a functional mastery here. We've gone past just seeing the numbers and we're into the procedural knowledge. You can now define all these systems, you know, the jargon-based, radix point, MSD, LSD complements, and you are fluent in the rules for base 2 arithmetic.
And crucially, you've mastered the conversion methods, the division and multiplication for going to and from decimal, and the fast grouping method for moving between binary, octal, and hex.
This is really the price of admission for technical literacy, isn't it? If you're going for an engineering exam or writing a policy memo on computing, you can't just gloss over this.
You can't. Knowing the difference between pure binary and BCD could be the difference between an efficient algorithm and a subtle, hard-to-find bug in a controller. Understanding two's complement explains the fundamental why behind a computer's design.
It's interesting. We spent all this time on the math, the arithmetic of it all, how much a number is.
Right.
But as we saw with BCD, the machine doesn't just calculate blindly. It has to make decisions. It has to check a condition. Is this sum greater than 9? Before it knows when to apply that correction factor.
Yes, that conditional check is a logical operation, not an arithmetic one. It's a true or false question. Is the sum greater than 9? Yes or no?
Exactly. So if these digital systems are just processing zeros and ones, and those represent physical states, what are the fundamental logical operations, the building blocks that go even deeper than arithmetic, that allow a computer to make those decisions, to decide when to add, or when to complement, or when to apply that BCD correction?
Well, that question right there leads us directly to the next essential step in mastering the language of digital systems: Boolean algebra and logic gates.